Hi everyone. So today we are going to look at the different bonding conditions that we encountered in heat transfer. Okay, but before that we need to understand few terms like what is Q and what is Q double dash. Okay, so this Q is basically the rate of heat transfer. Okay, uh, the rate of heat transfer, heat per unit time, the rate of heat transfer. Okay, the heat transfer per unit time. So it has a unit of joule per second. Joule joule is basically for heat, and time we have second, and this is also called as watt. Okay, so Q basically represents the rate of heat transfer, and it has the unit of watt. Then what is Q double dash? So this Q double dash represents the rate of heat transfer per unit area. This is also known as flux, and it has a unit of watt per meter square. Okay, it has a unit of watt per meter square. So this Q represents the rate of heat transfer, and this Q double dash, which is also called as flux, it represents the rate of heat transfer per unit area. Okay, now let's move on to the next slide. Now the first boundary condition is the specified temperature boundary condition. Okay, the specified temperature boundary condition. So let's see what it is. The first point states that the rate of heat transfer can be written as, okay, Q is equal to minus K dt by dx. This is basically the Fourier's law for heat conduction, where Q is the rate of heat transfer, K is the thermal conductivity of the medium, this A is the cross-sectional area, okay, and this dt by dx is the temperature gradient in the x direction. Okay, so as you all know, this is basically the Fourier's law for heat conduction. Okay, now let's look at here. So suppose that this is the slab, this is the slab, okay, and it has the two boundaries, one at x is equal to 0 and the other at x is equal to L. So, and suppose that at x is equal to 0 the temperature is given as T1, and at x is equal to L the temperature is given at T2, and the heat is being conducted through the slab in the x direction. This is the x direction, okay, this is the y direction. So the heat is being conducted in the x direction. Okay, the heat is being conducted in the x direction, and the rate at which heat is conducted is given as Q. Now look at the boundary condition. The boundary condition gives at x is equal to 0 temperature is equal to T1. At x is equal to 0 we have specified the temperature. Okay, so at x is equal to 0 the temperature is given as T1, and at x is equal to L we have specified the temperature as T2. So that's why this boundary condition is called as the specified temperature boundary condition, because at the boundaries we have specified the temperatures. Okay, so if we want the temperature profile, so we can put this equation 1 and equation 2, these two boundary conditions in this equation, the Fourier's law, and we will get the temperature profile. Okay, so this is all about the specified temperature boundary condition. Okay, now I hope this is clear. Now let's move on to the next slide. Now the next boundary condition is the specified heat flux boundary condition. Okay, so let's see what it talks about. Now the heat flux can be written as Q double dash is equal to minus K dt by dx. Okay, so we had the Fourier law as Q is equal to minus K A dt by dx. Okay, dt by dx. Okay, so if we divide both sides by the area, okay, if we divide both sides by area, then this will become the heat flux. Okay, it will become the heat flux Q double dash, and this area will cancel out, so we will have the heat flux as minus as Q double dash is equal to minus K dt by dx. Okay, so we have just written it here, Q double dash is equal to minus K dt by dx. Okay, so I hope this is clear. So the heat flux Q double dash can be written as uh, Q double dash is equal to minus K dt by dx. Now let's come to this figure. So this is the slab. Okay, and as in the previous slide we have seen, the slab has the two boundaries, one at x is equal to 0 and the other boundary at x is equal to L. But in this case the temperatures are not given at the boundaries. Either we have instead of temperature we have the heat flux at the two surfaces. Okay, one at x is equal to 0 we have the heat flux magnitude as q naught. Okay, and at x is equal to L we have the heat flux magnitude as QL double dash. Okay, this is the magnitude of heat flux. Okay, so at the two boundaries we have the heat flux magnitude. Okay, instead of temperature we have been given the heat flux magnitude at the two boundaries. So let's see about the boundary condition, that how do we write the boundary condition at the two boundaries. Okay, so we have seen the heat flux equation can be written as q double dash is equal to minus k dt by dx. Okay, now since we have specified the heat flux at x is equal to 0 and at x is equal to L, so we can write the first boundary condition as flux of okay, first read it, flux of magnitude q naught double dash is given at x is equal to 0, so we can write it as minus k dt by dx at x is equal to 0 is equal to q naught double dash. This expression is basically the flux. Minus k dt by dx is basically the flux. Okay, and the flux at x is equal to 0 is equal to the q naught double dash. Okay, so basically the flux, this mathematical expression states that the flux, that is minus k dt by dx, the flux at x is equal to 0. Okay, the flux at x is equal to 0 has the magnitude of q naught double dash. Okay, so I hope this point is clear. Now let's move to the second boundary condition. So let's see into the figure that at x is equal to L, the surface at x is equal to L, this surface has a flux of magnitude QL. Okay, this surface has a magnitude has a flux of magnitude QL. But one thing to note here is that suppose this is the x direction, this is the y direction. So as you can see in the first case at x is equal to 0, the surface at x is equal to 0 has a flux in the positive x direction. The flux is in the x direction only. Okay, in the positive x direction. Okay, but at x is equal to L, the flux is in the negative x direction, as we have assumed that this is the x direction, and at x is equal to L the flux is in this direction, so it's the negative x direction. Okay, negative x direction, and it has the magnitude of QL. Okay, so now let's see the second boundary condition. So flux of magnitude QL is given at x is equal to L, so we can write it as minus k dt by dx, that is the flux at x is equal to L is equal to minus QL double dash. Okay, this minus is been given because it is in the negative x direction. Okay, so I hope you have understood the two boundary conditions. So let's now move on to the next slide. Now the next boundary condition is the insulated boundary condition. Okay, so let's see what is the insulated boundary condition. So the first point states that if a surface is insulated, then there is no or negligible heat transfer through that surface. Okay, and if there is a negligible heat transfer through that surface, then the heat flux can be assumed to be 0 through that surface. Okay, so let's look into this diagram. So this is our slab. It has the boundaries at x is equal to 0 and at x is equal to L. Okay, and at x is equal to L the surface has been insulated, so this is the insulation at x is equal to L. Okay, as you can see this is represented by the blue color. So at x is equal to L the surface is insulated and the heat is transferred in this direction. Okay, this is the x direction, this is the x direction, this is the y direction. Okay, so the heat is being conducted in the x direction and the surface at x is equal to L has been insulated. Okay, since the surface at x is equal to L has been insulated, so the net heat flux through this surface is 0. Okay, because there is no heat transfer is being occurring through this surface. Okay, so the heat flux through this surface is 0. So we can write the boundary condition as, here let's see here, minus k dt by dx at x is equal to L is equal to 0. This expression means the flux, that is minus k dt by dx. Okay, this means the flux, and at x is equal to L, so the flux at x is equal to L is equal to 0. Okay, the flux is 0 because the surface is insulated, and the insulated surface does not allow the heat to pass through it, and since no heat passes through the surface, means the flux is 0 through that surface. Okay, so this is the boundary condition for the insulated boundary condition. Okay, so this is all about the insulated boundary condition. Okay, now let's move on to the next slide. Now let's see what is the boundary condition in case of thermal symmetry. Okay, so look at the first point. It states that in case of symmetry, the center plane can be viewed as an insulated surface. Okay, and at the insulated surface, flux is 0. So look at the diagram here. This is our slab with the same initial condition at x is equal to 0. One of the boundary is there, and at x is equal to L, the other boundary. Okay, this is the center plane or the mid plane at x is equal to L by 2. Okay, this total length is L, and this is L by 2, and this is also L by 2. Okay, so this is the center plane for this slab. Okay, now according to the first point, in case of symmetry, the center plane can be viewed as an insulated surface. Okay, so this is the left part and this is the right part of the slab. Okay, and as you all can see, there is a symmetry about this mid plane because the left part is identical to the right part. Okay, so there is a symmetry. So this is the case of thermal symmetry. So in case of thermal symmetry, the center plane about which the symmetry is there, that center plane can be treated as an insulated surface. Look, this is not a surface, but the center plane can be treated as an insulated surface. Okay, this slab only has a surface at x is equal to 0 and at x is equal to L, but this center plane in case of thermal symmetry can be treated as an insulated surface. Okay, so this is the center plane will behave like an insulated surface. Okay, and the center plane is at x is equal to L by 2. Now since this is an insulated surface, since this behaves like an insulated surface, so then flux through this insulated surface will be 0. Okay, because since this is insulated, there will be no heat transfer through this surface, and hence the flux through this surface will be 0. Okay, so look at the boundary condition here. It states that the flux, this part is the flux, and the flux at x is equal to L by 2 is 0. Okay, so this mathematical expression basically means that the flux at x is equal to L by 2 is 0. Okay, so I hope that this point is clear. So now let's move on to the next slide. So the next boundary condition is the convection boundary condition, and this is the most used boundary condition in the heat transfer. So let's see. So the first point states that a surface has 0 thickness and no mass, and since it does not have any mass, so it cannot store energy. Therefore, heat conduction at the surface in a certain direction is equal to heat convection at the surface in the same direction. So let's suppose we have a surface here and heat is being conducted through the surface. Okay, this is conduction and this is convection. Okay, this is convection, and this is conduction. Okay, so according to the first point, since the surface cannot store energy, the energy that is being transferred to the surface by conduction must be equal to the energy that is being convected out from the surface. So suppose 50 watt of energy is being transferred to the surface. Okay, then the surface must transfer 50 watt because it cannot store any energy. Okay, so the rate at which the energy is being transferred to the surface must be equal to the rate at which the energy is being transferred out from the surface. Okay, and suppose on both sides of the surface, like this side this is the slab, suppose this is the slab, and on the other side the liquids are flowing, the suppose there is a fluid stream, so the magnitude of rate of heat transfer will remain the same. Okay, but the mechanism of heat transfer will be different. Okay, so as you can see here, this is the slab, so there is conduction, and since this is a fluid stream, so there is convection. Okay, so I hope this point is clear. Now let's look at the diagram. So this is the diagram, this is a slab, and the slab has one of the boundary at x is equal to 0 and the other boundary at x is equal to L, and on the left hand side, that is before x is equal to 0, the fluid streams are flowing, and also after at x is equal to L there is a fluid stream. Okay, so at x is equal to 0, the fluids that are flowing, the fluids have a temperature of T infinity 1, and here the fluids have a temperature of T infinity 2. Okay, and the heat transfer coefficient, okay, let me change the pen, and the heat transfer coefficient between the fluid stream and the surface here is H1, this is H1, and the heat transfer coefficient between the fluid stream and the surface at x is equal to L, here this is H2. Okay, now since on this side here the fluid streams are flowing, so the mechanism of heat transfer is by convection, and since this is a slab solid, so this the mechanism of heat transfer is by conduction. Okay, now look at the surface at x is equal to 0. The heat that is transferred to the surface by convection must be equal to the heat that is transferred through the surface by conduction. So this is our first boundary condition. Now look here, the first boundary condition. So okay, first let me write the flux due to a convection. So we can write the flux due to convection as H, heat transfer coefficient, into the temperature difference, delta T. So the flux due to convection is heat transfer coefficient into the temperature difference. So for this case here, if we look here, we can write the flux as H1 T infinity 1 minus T1. Here the fluid stream has a temperature of T infinity 1 and the surface has a temperature of T1. So the temperature difference is T infinity 1 minus T1. Okay, and the heat transfer coefficient here is H1. So the flux here the so the flux, the surface at x is equal to 0 receives by convection is H1 T infinity 1 minus T1. Okay, now this is the flux due to convection, and the flux due to conduction at x is equal to 0 can be written as minus k dt by dx at x is equal to 0. I hope you all know this. Now since the surface cannot store energy, the flux due to convection must be equal to the flux due to conduction. Okay, so this is the first boundary condition, and similarly we can write the second boundary condition at x is equal to L. So if we want to write at x is equal to L, we will write the flux due to conduction at x is equal to L is equal to the flux due to convection at x is equal to L. So the flux due to convection at x is equal to L can be written as, look here at the second boundary condition, minus k dt by dx at x is equal to L. This is the flux due to conduction at x is equal to L. Okay, and this is the flux due to convection at x is equal to L. Okay, so this is the heat transfer coefficient and this is the temperature difference. Okay, the temperature difference is T2 minus T infinity 2. This is because the temperature is being transferred in the heat is being transferred in x direction. This is our x direction and y direction. So the heat is being transferred in the x direction. So the T2 must be greater than T infinity 2. Okay, so the temperature difference is T2 minus T infinity 2, and H2, this is the here the heat transfer coefficient is H2. So the flux due to convection is H2 into delta T, and here the delta T is T2 minus T infinity 2. So the flux due to convection is H2 into T2 minus T infinity 2. So the flux due to conduction at x is equal to L is equal to the flux due to convection at x is equal to L. Okay, so I hope these boundary conditions are clear. So thank you.